All right, we're live. It has been about 4 weeks since I've done my last stream. Just been really busy here lately during the day that I haven't really been able to stay here late taking care of some board repairs. Been trying to do them throughout the day just so that we can get turnaround times done a little quicker. But today we have a very interesting one. We have a MacBook that fell into the bath. I don't know the logistics. That's all I was told, that it fell into a bathtub and it's no longer turning on. So let's go ahead and see what happens when we hook it up to our ammeter, our USB-C ammeter. And for this, we're going to need a known good USB-C charge port. So if this computer is working, what we want to see is 20 volts at roughly 0.6 amps to 1 full amp. This one is a 2017 15-inch. And let's see what our USB-C ammeter says. 20 volts. Interesting. But at 0 amps. That's 0.04. So we are getting 20 volts, which means that our CD3215 is working. Fascinating. Let's see what's going on over here. Still, same thing. So we're getting 19 volts, but we're missing we're missing our amperage. So we're only getting about 0.05 amperage, which is very nominal. Basically, it's not enough for the computer to turn on. So this model, let's check and see if we even have the schematics available for this one. I think my mouse is dying. That's exactly what's going on. 1 second. Good morning from Philippines. Thanks for joining. It is 9:40 p.m. over here. Or 21:41 depending on where you're from. Did I say that right? No. I didn't. Okay, do we have a working... Oh no, did our eye die? Okay, there we go. Nope, and it's gone. Must be the surface. Oh, looks like this is turned into a mouse repair. I'm sorry for the technical difficulties. Okay, that's not working. 1 second. The mouse was working perfectly fine earlier. Let's see. There we go. We actually had some interference on our USB bus. We're back in business. So let's check and see if we have the schematic. And which model is this one? Definitely see a lot of corrosion around one of our CD3215s. This one is an 820-002-00928. Not bad. Alright, so let's check and see if we have that. What brand is your overhead camera? It is a Logitech. I think it is the C920. They're really hard to find right now. They used to only be $40 before the pandemic. Okay. So we said it was 820-00928. Well, we have the board view that popped up, but we don't have the PDF. Why is that? And tonight's just going to turn into a stream of, let's see if we can fix our own tools. So, let's see. Now it has the schematic right here. Well, our Flex board view seems to be having an issue reading or opening up the schematic. That's not working. Let's see. Go to File. There's the board. Alright, well, we're going to have to do this the old-fashioned way then. Just pull up our own Sumatra PDF viewer. So, from my past experience, whenever we've gone 20 volts, that means that the charging chip is properly talking to the CD3215 and turning on the rest of the device, but we're missing some other power rails. So I want to check and see our other power rails that we have here. And that's going to be located under power aliases. So here on page 1 of power aliases, do we have PP bus? We're going to have to do this the old-fashioned way, just like with the free version of Flex board view, which is an open board view. So we'll copy, find, paste. All right. Now, let's switch over to our actual microscope and inspect what the board looks like. I've only seen this with my naked eye. Let's get our camera in focus. That looks good. And let's see what we have. So there is a lot of damage around here. And normally when a board is this damaged, it's going to be strictly data recovery, because we can get it working, but there's a lot of corroded components. So while it will work for a little bit, it's kind of hard to ensure the longevity. Alright, so the Hall sensor's got a little bit of corrosion around it. That, whatever that is, has a lot of corrosion. Yeah, this one looks pretty bad. Our backlight circuit looks, or those capacitors look pretty oxidized. Even our charging circuit, surprisingly, the ISL is still working, despite it looking pretty brown. Okay. All this just looks like a fun mess. Alright, not to worry. Let's go ahead and hook up our ammeter and measure for PP bus. So when our board is in our orientation like this, we'll measure this capacitor over here. So let me grab my charger. And now we can switch over to the microscope camera. And we want to measure this capacitor, which is right next to what I assume is an audio chip. And let's see if we have PP bus. We don't. So PP bus is being pulled down. We have 2 volts. That's not right. And just to make sure, let me make sure the charger is actually plugged into the USB-C charge port. Okay, just turned on, got 20 volts, and let's measure again. Okay, so it just looks like that my charger wasn't in all the way. We're getting 12.6, so that is PP bus. Now, let's go back to our schematic and move on to the next line. So PP bus is all present. And this is going to be PP bus high side GPU, which we're really not too concerned at this moment. I'm pretty sure our PP3v3G3 hot rails are present because that is what initiates the CD3215. Let's just double check because I want to make sure I'm spouting the right information. So right next to where our battery typically plugs in, looks like we have an area that we can measure. And these 2 capacitors right there in the center are going to be our PP3v3. And that is what we have. Real-time clock rails. This is necessary in order for the clock to properly turn on. This one's a little bit smaller, but it's right next to our U7800. Looks like we should be able to measure that. And do we have 3 volts? We do. We have exactly 3 volts, so that looks to be perfectly fine. Okay, and then this is going to be our SO rails, the CPU, or this one specifically is what powers the CPU, the PPVCC SO CPU. I have a feeling this rail is not going to be present just because the rest of the computer is not pulling any amperage. So I feel like we're going to be missing some S4, S3 rails, maybe even some S5 rails. And it looks like we have some shunt resistors up here above the CPU. Let's see if we can measure for that, just to make sure that we're not going into an SO state. Yep, nothing at all. So the computer is not going into an SO state. So we have at least our PP bus and we have our PP3v3. Now we just need to, at this point I normally would do a visual inspection, but there is so much damage that I don't know where to start. So that's kind of why I'm going through the power aliases to kind of figure out if there's a rail that's missing. So let's see what else we have. Because this is just page 1 of our power aliases. So we're going to have our 1.2 volt lines. I don't think those are going to be present until it gets a little further down. Yeah, it looks like this is going to help with the CPU. So let's check our other power aliases. This is going to be our 1 volt rail, 5 volt, and 3 volt. Let's check and see if PP1V0 sus is present. I think that's sustain. And let's see. We won't be able to access that because that's underneath our heatsink, but we have this tiny, tiny little capacitor, as well as this tiny little capacitor over here. Let's see, and it was near our coils. Okay, that's one right there. Let's see if you have 1 volt. I don't think we're at that point just yet. Nope, that is not present. Let's start a little bit higher. Instead of working on our PP1V, let's check our PP5ES5. Just because it's a higher rail, that will eventually break its way down. And looks like there's a test point on the top part of the computer, and all around, and this is going to be what generates our PP5ES5, probably even our PP3V3S5. Let's flip the board over and take a look. Let's see. Yeah, so there's a lot of oxidation over here as well. But that's kind of the entire case with this computer. So, do we have our PP5ES5? It would be this pad right here. Yep, we do have 5 volts. Do we have PP5ES4? And normally you don't have to copy and paste with Flexboard View, but it looks like with this schematic specifically, something's not working. So we're just doing it the old-fashioned way just for this stream. Alright, right next to our U7650, we have a C7608. Does that have 5 volts on it? Are we going into an S4 state? And that's going to be that tiny little guy right there. Do we have 5 volts? We do not. So we are not going into an S4. So we're still missing, potentially, some S5 rails, which is preventing the computer from turning on. Let's check and see if we go back to our schematic here. If any, we know that our PP3V3G3 hot is present, but what about our PP3V3S5? Alright, so that's a little bit of everywhere. These giant capacitors in the general area we look like are responsible for our PP3V3S5. Let's see, do we have 3.3 volts? And we do. So at least that isn't an S5 state. Do we have our PP3V3 sus? Tiny, tiny little resistor in the same area, but let's measure it. Yep, that is present. So we do have our PP3V3 sus. I think that stands for sustain. Or suspend. Sustain is a musical term. Suspend. Let's check and see, do we have our PP3V3S4? Around our Wi-Fi, looks like we have a couple of S4 lines. A tiny little capacitor right here is part of that line. And it is not present, which I'm not surprised, just because our S4 was also not present on the 5 volt line. Okay, this one is starting to get interesting. Let's find out what else we got going on. So if we're not going into an S4 state. Let's see if I can remember where we should go from here. Because if we're not going into S4, in previous models, what you would do is you would check and see what the PM sleep line was. So you needed PM sleep S4 to be present in order for S5 rails to cut down into our S4. Then PM sleep S3 would then turn on our S3 lines, PM sleep S2, PM sleep S1, until eventually the computer turns on. It's kind of like a chain or a waterfall of things that have to occur before the computer turns on. This one's a little bit different. Let's think. We could just do a visual inspection. And we did have a lot of junk over in this general area. What is this component responsible for? Let's find out. It is U2890, and we have to look it up the old-fashioned way. Oh man, U2890. It's been so long since I've used this PDF viewer. Wrong next button. All right, this is going to be, is there any other information on here? USB-C high speed. Whatever it is, it talks to the SPI or the BIOS. We have our clock, our current sensing. What is this? Machine. I think this stands for master out, slave in, master in, slave out. So this is going to be kind of an important chip that talks to the BIOS. Okay. What else do we have? I mean, just that in general just looks bad. Just need to reflow the entire board. I'm just kidding, don't do that. Yeah, that one's just bad too. It's interesting to try to figure out what is bad. I mean, it's all obviously bad, but what is the signature bad part that is preventing the computer from turning on? These CD3215s look really bad as well. That was loud. Let's find out if it's going to power on this side. Now, how the CD3215s work is if one chip doesn't work, the entire computer doesn't work. Which is surprising because all these chips look bad. So I'm just plugging it on this port just to see what happens. Interesting. Okay, so we have 5 volts on this side. We have 20 volts on this side, 5 volts here. So maybe it's not turning on because we actually do still have an issue with the CD3215. The fact that one turned on to 20 volts, though, is interesting. This one's got 20 volts on this side as well. All right, come to think of it, I didn't even test this other port over here. I have 20 volts, 0 amps on this side. $20 volts, 0 amp on this side as well. So this specific port, when plugged in, let's see if it gives us 5 volts again. And we can kind of inspect around this CD3215 and see if it's responsible as to why we're not getting any amperage consumption. 5 volts. All right, so definitely a finding. Okay. So that's going to be on this port. If we zoom in, we should be able to see if this is a or which port exactly this one goes to. Okay, it looks like it may be our UB300. And usually you can actually read because they have them marked in A, B, C, and D. So USB-C Thunderbolt DTR. Okay. So, if I had to assume, this is going to be an assumption, it's going to be this one, the one on the right side. And we should be able to measure. In fact, what I'm going to do, I'm going to use a little cheat sheet here. And let's check out LogiWiki real fast, just to see if our LDOs are present for this specific CD3215. So what we want to scroll down for, this is a great website hosted by Chris over at Shiny Computers. There is a lot of information here that a lot of techs on the Rossmann Discord have pitched in together. And what we want to do is check the startup sequence here for this specific CD3215 and kind of see if this points us in a direction of where we want to go. So what we want to look at is check and see, are we even getting 5 volts on this bus? I feel like we are, just because our USB-C ammeter turned on. We'll confirm, but we also want to check to see if this PP3V3 UPC XB, this one might be XD or XC, LDO is present. So for now, let's switch back over and open up. Oh, that's right. The schematics aren't working like they should. So we need to look up our UB300. And so these are going to be all the LDOs. And so the one that we wanted to look at is going to be, this one's different. It's called PP3V3 UPC TA LDO. So let's find out if that's present. And that should be, in fact, hold on, was that the right one we were talking about? Yeah, so that's going to be our 3 volt line, our 3.3 volt line. And it looks like it actually runs through this component as well, which was equally dirty. Okay. In fact, we can actually see that this specific pin right here on the far left is connected to that 3.3 volt line, and it looks pretty destroyed. So let's hook up our power into it and see if we get our 3.3 volts. And in fact, let's look back at the schematic to see, or the board view to see where that connection is. So we have this capacitor right next to this component, and let's get a measurement. Do we have 3.3 volts? We do not. In fact, I'm reading negative 0.001. Let's check and see if that is a short. Put my multimeter into resistance mode, and when we measure this, nope, it's in the mega ohms. So every port has a different CD3215. So I need to make sure that I'm even talking to the right CD3215 chip. So what I was doing was hooking up my charger right here, hoping that it would talk to this chip, and we're not getting any power. Just to kind of rule out, make sure that is the right component. I'm going to plug in our USB at the top, and I'm going to measure this one more time to see if we are getting that 3.3 volts on that LDO. We are. So I was wrong about the chip. So this is actually responsible for the top USB port, not the bottom, which means I was wrong on my CD3215. So this port is actually responsible for this CD3215. All right, we made a little bit of progress. Let's move on. So now we will pull up our UB400 into our schematic and check our LDOs from there. All right. Such a weird PDF viewer. I'm so used to the Paul Daniels PDF viewer, but it's not working tonight. So this one is PP3v3 UPC-TB. So that, the other one was TA, this one is TB. So let's measure this capacitor to see if we're getting 3.3 volts. And it's that really corroded, oxidized looking capacitor in the top left. Are we getting 3.3 volts? Amazingly we are. Cool. That is a Christmas miracle. So now let's go back to our cheat sheet that we have here and check and see if we have this PP1V8 UPC-XB LDO-A. Ours is going to say TB instead of XB. Something along those lines. Let's see. V8. Yep. So it's this one right here. And the reason why I'm not copying and pasting everything that's from the Shiny Wiki is because that is just kind of a template from a different logic board, so it doesn't have the exact same net names as the board that I'm working on currently. Okay, so this tiny little capacitor right here, let's see what it is pulling. And if I had to assume, given the net name, 1V8, this is going to be our 1.8 volt line. It'd be nice if you could actually see what I was looking at. And that is surprisingly present. All right, moving on to our next LDO. Let's go ahead and check this one right here. Our UPC, our PP1V8 UPC-TB LDOD. Up here on the very top. 1.8. All right, so that's there. So that's 3 down. Let's check this one. Our PP1V1 UPC TBLDO BMC. That is a lot of abbreviations. No, come back. Sorry, you couldn't see what I was saying. I need to get one of those like launch pads almost to quickly switch scenes here. Okay, so this is going to be 1.1 volts. Nothing. Let's try that one more time just to make sure that I wasn't missing. In fact, it actually almost looks cracked. Alright, so that is not turning on. So let's check and see, is that shorted or partially shorted? Nope. It is in the kiloohms, which means it's probably just not getting power. Okay, let's reference and just make sure that that indeed is one that's supposed to turn on. It looks like it is. Yep, that is one that is supposed to turn on. So this one is missing. So if this is missing, then we're not going to be getting step 3 and continuing on from here. So I want to see if maybe this is just a dirty connection. I will apply flux to the area and just give a reflow back onto that specific CD3215. But before I do that, there are a couple of heat shields here that I think need to get removed. This one in particular. So right now, what my theory is because this one specific CD3215 is partially turning on, but not actually turning on all the way, the computer as a whole is just not booting up. Okay, so now with this removed, let's go ahead and apply some flux. Also, I need to turn on my fume extractor. And just have a sip of coffee beforehand. There's just so much corrosion throughout the board. I don't want to give it an ultrasonic cleaning because that would just remove any hints of where our damage is located. But at the same time, I don't want to just reflow all the corroded components because it seems, despite them being gross, white and blue corrosion looking, for the most part, the other CD3215s seem to be operating like they should. But this one is not. So what we'll do is we'll heat up the area until we can see the chip dance. That's what I like to call it. We'll actually see it kind of wiggle into place. Because once it moves, that means all the solder balls underneath this specific chip have moved enough to reflow or reball themselves essentially back onto the solder pads. There could be some oxidation that is preventing a clean connection. If this doesn't work, we do have replacement ICs that we can put in its stead. And you see how it's like doing that little dance? So it has been reflowed. Now let's just wait. In fact, one little trick we can do is just put it up right here to your fume extractor and wait for that to cool down. Okay. And that's cooled down enough for us to be able to test and see if that fixed anything. Are we going to get our 1.1 volt line? Let's see if we have any change. Are we going to get 20 volts? We're still getting 5 volts at 0.07 amperage. Basically nothing. So that doesn't look like it really solved anything. So we're probably going to have to end up replacing that. Let's get a measurement one more time, just to make sure that this is supposed to be turning on. Aha! We have 1.1 volt. We've made progress. So something else is going on here. So this is another interesting when it comes to computers that are this severely damaged, is that we might fix one thing, but then there's another something that's preventing us from continuing on from here. So we now have our 1.1 volt on this specific CD3215, our TB on this specific model. So I'm going to go back to the cheat sheet here on the LogiWiki and see what we should be looking at, because we do have all of our LDOs. Let's switch this back over. So now we want to see if we have our HV gate 1 and 2. High 5 volts, later 20 volts. So that is going to be on this specific board that's being used, our U3200. But I don't think that is the same chip. In fact, actually, this is all going to be pertaining towards U3200 on this specific board is a CD3215. So HV gate 1 is going to be on our IC. So let's check our schematics here and see, look for our HV gate 1. Where are you hiding? I'm sure it is right in front of me. We have our UPC TB gate 1. I wonder if that's what's similar. Let's check again. HV gate 1. I want to say that's what this is. So our QB400 takes 20 volts. This is just a fancy, very fancy MOSFET. Yep, right here, my bad. HV gate 1, gate 2 is going to be B9 and A9. So let's find out if there is any power on that line. So that is going to be UPC TB gate 1. Where are you located on our board view? You are going to be, we got a test point right here. In fact, we actually got QB400 right here. So let's switch over. And Oh, wrong microscope camera, or just wrong camera in general. Sorry, just fixing my setup here so I can see better. Okay, so our test point is going to be this right here. And let's see if we have 5 volts. Interesting, we have 10. That doesn't seem right. It almost seems like that's too much power. So to confirm, what I'm going to do is cross-reference with our other CD3215 and measure its QB3, which is going to be up here. So the test point for that one is directly to the right. .10 volts. In fact, actually now, as I'm looking at our charger, we have 5 volts. So it looks like we did something to a CD3215, and maybe it was to both, but they're not working. Awesome. Okay. That's kind of progress. I think we're just ultimately going to have to replace both of these. They look pretty bad. I want to see what it looks like when it turns on. So I'm going to compare it to another CD3215. Nope, this one has 5 volts as well. Awesome. So we triggered something. Looks like we may have found the defective CD3215 that is preventing the rest of them from turning on. Cool. I'm just going to go ahead and replace the one that we reflowed. So that one right there. Let's go ahead and pop it off. Because after we gave it a reflow, that's when all of the other chips quit working. So I almost feel like this chip was bad, but it was disconnected per se. And after we reflowed it, we reconnected it onto the board. And we'll just say we put it in series with the other CD3215s, which are now turning themselves off because this one may be pulling it down. That is a horrible layman's explanation of what's going on here. But that's kind of what I'm understanding it to be. Alright, so looking at the chip, I don't see any immediate signs of gunk. But while this is still hot, let's wick up the solder pads. So now that we have our solder pads cleaned, let's get ready to put some new chips on. And let's make sure that we have some new chips. Hold on. It looks like I just haven't actually gotten around to putting them away. We do have some right here. Here they are. Are these the one that we have? Because there are a couple of different kinds of CD3215s. This one is a COO. This one here is a BO3. That's not the right one. COO. Awesome. Yep, that would be it. So let's prep our area. What I mean by that is I'm going to put just a tiny little bit of flux in the general area where the solder pads are going to go. And afterwards, we're going to hit it with some flux just to spread it out. I'm sorry, hit it with some heat to spread the flux. And once that has been spread, let's put our IC down. And for this specifically, I'm going to drop the airflow on my quick so that it doesn't blow away my IC. In fact, it actually looks a little low compared to the other chip, so let's raise this up some. This way does take a little bit longer to solder it back onto the board, but the board is not going to fly off into my fume extractor. Alright, that moved a little bit. So it should have grabbed onto a pad. Now let's just hit it with a little bit more flux. Come on. And let's turn up the airflow some now. Alright, the chip as a whole is moving around, which means we should be good. All the points are soldered. Let's wait for that to cool down, and we'll test and see if that made any progress. Let's see if that changed anything now that we have the new CD3215. Nope, something else going on here. So we still have 5 volts. And let's see if the other ports have 5 volts. Yep, same thing here. Alright, so something is not turning on. And I could just meticulously replace every CD3215 since they were pretty corroded. In fact, the one on the right side was the one that I said looked the worst. And if we look at, it would help if I had the right camera on. And if we switch over here, this one looks pretty bad. And let's check and see if we have that 1.1 volt again, just to make sure that this is properly installed. And so it was this capacitor in particular. We have 1.1 volts, no problem. So then the next thing we wanted to check was going to be our HV gate 1. And I think earlier when we checked it was around 10. Specifically, it was this point. Do we have 10? We do. We do have 10 still. Alright. For this specific board, being that it is a 15-inch touch bar, A1707, and the other one that looks like was used in the template here, is more than likely a 13-inch. In fact, it actually says right here A1706, so this is going to be the 13-inch version. I'm going to say that 10 volts may be normal for this specific model. So I'm just going to move on to the next thing and check and see if our PPTC and G3 hot is present. I'm pretty sure it was because the unit itself is getting 5 volts. And we'll measure this side of QB400. Yep, 5 volts. TBA VDDA. Let's see if we have anything that looks similar on here. Not seeing anything similar to that line here. Unless it's not around the CD3215. Let's see. Definitely please burrowing here. Oh, the line does exist, but where? Okay, it's actually going to be next to our U7000. Let's check it out. Yeah, I mean, it doesn't look the best. Okay, so that specific line, the TBA, is going to be right here. 5 volts. It looks so bad. Okay. Probably gonna end up replacing it, but let's confirm some more before we keep going. There we are. Here we are. PM enable P3, P3, G3 hot, which I'm pretty sure we've already measured. It's already there. And it's a no surprise. That also looks pretty bad. Five volts. And then we've already made sure our PP333 hot was present. In fact, let's make sure it's still working because we reflowed that CD3215 and our 20 volts went away. It's actually 3.4, and which seems a little high, in my opinion. It might be okay, but it still just seems a little on the higher side for me. Okay, before we go any further, I'm just going to go ahead and replace our U7000. It just looks like it's going to need to be replaced anyways. Especially if you're going to be doing any data recovery. I don't want this to just go out on me. So this is going to be our ISL 9239, which we should still have a couple of these in stock. It's actually taken quite a while for it to heat up. Curious if that's because it's just heavily oxidized on the bottom. For the most part, that side looks okay. Let's see what the bottom side of this ISO looks like. There's a little bit of gunk. I don't think that was enough to have a bad connection, but everything else around it looks gross. So we're just going to replace it. Alright, now let's get our replacement ISL. Alright, we got it. So just like earlier, let's put a little bit of flux over here and heat up all the pads. Not like that. Wrong orientation. Okay, and let's lower our air throughput so that we don't accidentally blow away. Especially with a chip this small. Yep, there it goes. But it went to the side. It didn't actually go into the fume extractor. Let's try that again. Nope. Nope, there it goes. Oh, sad. Okay. Looks like we're gonna have to use just a little bit more flux to hold it in place. Just in case, I'm going to drop the throughput just a little bit lower. I think the technical term is CFM. Alright, so now it's starting to solder, which means we can increase our air again. And then just so we don't start oxidizing too much over here, let's add some more flux. Perfect. All right. Meanwhile, let's see if we can study up on what this is responsible for. let's find all our information about our U7000. Okay, so this is going to be our U7000, and it is responsible for sending or creating PP bus, which is going to send, yeah, this creates our PP bus. So it receives power from PPDC and G3 hot, which makes its way all the way through a series of shunt resistors and MOSFETs, which then turn on U7000. Looks like it gets a couple of signals from the SMC, and then it creates PM enable P3 G3 hot, SMC reset L, and eventually makes its way to creating PP bus. Okay, so yes, this creates our PM enable PP3v3 G3 hot, which is a power line required for turning on our CD3215s. Now that was already turning on, but I'm just curious if maybe our U7000 was damaged and not talking to something else on the SMC. Okay, that makes a little bit more sense now. So let's flip back over and check and see if our board has cooled down enough. Okay, looks like it has. Let's put these away before we lose these. And see what kind of progress we have now. Still the same, which I kind of expected. I just wanted to clean that area up anyways, because it looked like garbage. Alright, well, let's find out if we're even getting PP bus now, after doing all that. Okay, so we have PP bus over in this general area. And what do we have? Aha! PP bus is not present. We have something that's pulling down PP bus. 0.7. Alright, so now this is the part where we can use our thermal camera. I guess my question is, PP bus, it is present whenever we don't have... Hold on, let me check something else out. Because we don't have 20 volts. But yeah, something was definitely pulling PP bus down. Okay. So let's open up our Keon Lee Thermal Imager software to see if we have a partial short somewhere on PP bus. In fact, I'm getting a little too ahead of myself. We should have measured to ground the resistance, or impedance I should say, of our PP bus to see if something's pulling it down. No, we're in the mega ohms. So it's not necessarily shorted, but something is definitely pulling down PP bus. Okay. That could have been dangerous. For those of you that did not see that, my microscope tried to fall forward just now. Fortunately, I caught it in time. Okay. Back onto this. And I expect this to be very, very choppy since we are streaming on a Intel Core 2 Duo processor, while also trying to search for any instance of heat. Definitely is slow. Now this general area is still going to be warm just because we were heating it up with our rework station. But there is one spot in particular it's showing that's pretty consistent over here. That is 5 degrees warmer than the rest of the unit. And let's keep looking. We'll revisit that in a second. And the reason it's so choppy, I'm just moving it a little bit at a time. But also, it's just too much processing. I did get some components for building a new streaming computer for Cyber Monday. I'm just waiting for them to come in. I was looking for new graphics cards, but it almost seemed like with Black Friday and Cyber Monday, graphics cards went up in price, which is the opposite. And I know that's because supply and demand are a factor in this case. But I was looking at the NVIDIA GTX 1660, and no, it's not the best, but just enough for streaming. That's really all I need. And the card is normally $240, and they're sold out everywhere. The cheapest I could find was $500 off Amazon. So I'm postponing getting a new graphics card for the time being. Okay, so it makes sense that that CD3215 is getting warm because that's where we're actually connected to. All right. Let's flip the board over. And everything that is reflective, all the heat plates, they're going to make it look like it's reflecting the FLIR or the infrared back at itself, so it thinks it has more heat than there actually is. Okay, this is painfully slow. Okay, let's look near the top of our CPU, or in the orientation I have it's going to be below it. Okay. Nothing that's really jumping out on me on that side, but back over here, there definitely was some components that were jumping out at me in this general area. So this part of the computer is, or this part of the logic board is about, it's very small. It's only 4 degrees difference. Let's see if we can turn off our thermal imager just to see exactly what that is, and that looks like this is going to be a diode, and okay. Alright, enough looking at that for now. Let the stream get a little bit smoother again. Alright. So the component that was getting warmer than everything else here is this diode, which is, my understanding, the diode of PP3V3G3 hot. So that might actually be normal, but this, it's just all dirty. Okay, let's pull this up on our schematic to understand how this area works. So if we make our way over here, D6902, and you'll have to pardon me for 1 second. Okay, sorry about that. Just had to take a phone call real quick. So if we switch back over here, so the component in question that was getting hot is PPVNG3, PP3V3G3 hot. Alright, so it is a diode, and on one side is our PP bus, and the other side is our PPDCN-G3 hot. Now, when I checked earlier, our PP bus looked like it was being pulled down, and that looks like that's over on pin 2, so let's measure that one more time to see if something is going on here. So PP bus on this model is roughly 12.6 volts, and I'm getting 0.7. So that is not correct. Let's make sure that this diode is working like it should, so I'm going to put my multimeter into diode mode, and we should hear a beep on one side, but not on the other. So there's a beep on there, and then we're good here. A beep on this side, and okay here. So it looks like this might be fine. So something probably either before or after this diode is pulling voltage down. So what I'm going to do for the time being is just temporarily remove this diode and see if our PP bus is going to come back. And for this, I'm actually going to use some tweezers, just so I can kind of heat up all the pads at the exact same time. Alright. Looks like that this diode might be a little bit too big, so we'll have to go back to the old method of just heating it up with our rework station. Alright, so with that diode completely removed, let's check and see if we have normal PP bus on pin 2. Still 0.6 and being pulled down. So PP bus is not making its way over here, so this isn't our area that is damaged. In fact, actually, let me just double check that that is the correct one. So pin 2, yep, right here, goes through this resistor, PP bus G3 hot R, is not getting enough power. But we do have PPDC and G3, from USB-C source. Okay, so this would probably be from our battery, and this is going to be from our charger. Oh, that's probably normal then. Let's turn this back on and see what the other side is saying. I'm getting 5 volts, just a solid 5 volts. Why are we getting 5 volts? Of course. We may be getting 5 volts just because our CD3215 is only pulling 5 volts. Or requesting 5 volts. This one is... I'm forgetting a fundamental step. I know I am. Just need to remember what that step is. Oh, I had a feeling it was going to happen. Where'd you blow off to? Alright, you need to go back to your little home diode. Oh my goodness, okay, so my CFMs on my quick is just a little bit too high tonight. Let's see, where did that blow off to? All the way over here. Let's just put you back in your place. Okay, so with that back on, let's check and see what pin 3 says. Five volts. Okay, so it looks like everything on the circuit's perfectly fine. Think. Been going for an hour and a half and still in the preliminary phase. Okay, PPDCN G3 hot, USB source comes. Let's see what our PPDCN is. It's probably going to be 5 volts just because that's all that the CD3215 is requesting. And I feel like if that's all it's requesting, then our PP bus is not going to be the 12 volts that it needs to be. Alright, so we're looking for the shunt resistor right here, just to see what we're reading as far as our PPDCN, or our DCN. So let's switch back over to our microscope camera. So pin 2 and 4 over here on the left side is going to be our PPDCN. Let's check and see. Is it 5 volts? That would be over here. Yeah, 5 volts. So that's my assumption here, is that we are not getting PP bus to be anything higher because our CD3215s are only requesting 5 volts instead of 20. Now, the strange thing is our USB TB was originally taking 5 volts, and then we gave it a reflow just because we were kind of going down the hierarchy of steps necessary for it to request 20 volts. And then it still continued to receive 5 volts, but the rest of our CD3215 started request 5 volts. I'm almost curious if the CD3215 next to that one was equally as bad, and when we heated it up, we actually broke a connection. And we need to get the CD3215 to request 20 volts. Because when we were going through, we were missing our PP1V1 UPC TB BMC, and then after we give it a reflow, it started working again, but everything else stopped working. So let's switch over to the other CD3215 and kind of check these LDOs to see if they are present as well. Let's see. So that was this one, UB300. UB300. And here are going to be all of our LDOs. So this one is UPC-TA. Let's check and see if we have 3.3 volts on our UPC-TA LDO. We should, because we do have a working ISL. We did replace it just in case because it did look a little on the barbecued side. Alright, so this giant capacitor right here to our top left. Are we going to get 3.3 volts now? 3.3 volts, perfect. Alright, move on to the next. Do we have our 1.8 TA LDOA? That's not what you were supposed to do. You're supposed to show me, not disappear. And we have a test point at the bottom of the CD3215. .8 volts. That is present. Do we have our PP1V8 UPC-TA LDOD? Whew. .8 volts. And do we have our 1.1 volts? That's going to be that capacitor in the middle to the left. 1.1. So as far as our LDOs go, that looks like that pretty much covers them for that specific IC. Let's think. And then our HV gate 1, I think when we took a look at that, that was roughly 10 volts on this specific model. And that's going to be connected to HV gate 1. There's UPC-TA gate 1. And there's a test point right here to the right side. $10 volts. And then our gate 2 is right above it. 7.2. That's an odd number. I think what we're going to have to do is compare that to our other CD3215. So let's check and see. So this test point right here is supposed to be gate 1 on our TB. 10 volts. Okay. And then we have another test point all the way up here somewhere. Actually, hold on. Where is it? Right there. $3.3. So the other one was 7. This one's 3.3. Now 3.3 is an actual number that I'm used to seeing, but that 7, that is a strange number. So, could this be our issue here? I need to confirm by flipping this charge port over onto the other side and inspecting the CD3215s over there and see what our gate 2 on them looks like. And if it's roughly 3.3 volts, I'm gonna look into see why that MOSFET is pulling 7 volts, because that definitely is an odd voltage. And this is where I waste time just being a little precautious, just double checking why a port is taking, or why a chip may or may not be working. I just want to make sure we're not just randomly throwing parts at this and seeing what sticks. Okay, let's make sure that this is the right connection. Alright, so U3100. Let's see. Oops, still too used to Flex Board View software. That's not working right now. At least the PDF viewer is not. And let's check our UPC XA gate 1. $10 volts. Alright, so 10 volts looks like that's actually pretty standard for gate 1. Let's check and see what our gate 2 says. $7.2. Okay, so we have something in common. This is actually putting out 7.2, the other one was 7.2, so maybe that's actually normal. Maybe the 3.3 volts on the other side was weird. Just to confirm, one more time, let's plug this into a different USB port and check and see what the measurements are there. Okay, back onto the schematic. So that is U3200. Something looks a little off in this area compared to the board view. But we do have a probe point up here above this specific gate. So let's see what we get. 10. Okay, so 10 on gate 1 looks to be the common denominator here. Now let's check and see what we have as far as our gate 2. This one's going to be a little bit harder to reach, just because it's wedged right next to that cowling, or the covering of this SSD. 7.3 specifically. All right, so it looks like that 3.3 volt that we had on the other side is the is singled out. There's nothing else that I can find compared to all of those other MOSFETs for the gates that are reading 3. Everything else is reading about 7. So let's inspect why it's possible that one is reading 3. And if I recall correctly, that was this right here. Probably connected to the wrong port. Okay, now that we are connected, let's check and see what are we reading right here. 10 volts, and then gate 2 is all the way up here. 7. What? I'm getting trolled here. That was the same one I measured, right? Hold on. Probably not. Let's double check something. Maybe it was this one that was reading 3. Nope, 7. What? Why are we getting some inconsistency? Okay, I feel like I'm going down a rabbit hole at this point. What should we look at next? Okay. We already know that PP3V3G3 hot is present. Let's check and see if our PP1V2G3 hot SMC VDDC is present. Okay, does not look like that is a exact name for this specific model. Let's see. PP1V2G3 hot SMC VDDC. For this specific model, it was U5000. Let's check and see. Do we have a U5000 on this model? Usually with a chip that big, it has a very similar name. Okay, looks like this is going to be something to do with potential power to the SMC, which if I recall, when I looked at that area, it did look pretty oxidized. Let's see, what are you? You are the SMC. Oh. Okay. Let's go take a look back and see if that signal that we were looking for, if there's a similar name, PP1V2 G3 hot SMC VDDC. And VDD is going to be a power line. Is it going to be similar to this, PP1V2? What did we have here? That was G3 hot. The other one was an S5. So do we have a G3 hot signal? Because it might not be present. It might just be S5 on this model. Let's find out. Giving it a quick little skim through. SMC shared support. And that's kind of what it looks like. In this model, it doesn't have a G3, it has an S5. So this is what's going to power part of it, the VDDC for SMC, the 1.2 volt line. So let's see if that's present. Let's switch back over to our microscope and check and see what exactly is going on over here. If I recall correctly, this area, oh, whoops. If I recall correctly, this area just looked really, really poor earlier. Yeah, we definitely have some corrosion right there. Interesting. To be honest, I actually haven't had to mess around with the SMC on an A1707, so this is actually news to me. So let's take a look. 1, 2, 3, 4, 5, and 6 from the right look really messed up. So let's take a gander back on our board view. So we said 5 and 6. 1, 2, 3, 4, 5, and 6. So we have SMC sensor power enable. That looks like that's needed to turn on, and I'm actually not too sure what that one is. SMC OOB1R2DL. Alright, well what we were looking for originally is going to be that PP1V2 S5 SMC VDDC. And let's see if we have 1.2 volts. Ooh. Actually, as I'm looking a little bit more up here, looks like we have some more stuff around that specific component. But before we get too distracted, let's go and find out if we have our 1.2 volts necessary to even power our SMC. Make sure that's 1, 2, 3, 4. Yep, we are missing 1.2 volts because we do not have our power supply connected. Oh man. And this is just one of many repairs that are going to be worked on tonight. Let's do that all over again. Alright, do we have 1.2? Yes, we do have 1.2. Okay. I think the next step is going to have to be to reflow our SMC just because of the corrosion that looks to be bridging our SMC sensor power enable. Because let's see what the next step was after that. That would be our PP3V0G3 AV reference SMC, which, let's see, does that come out of our SMC? Where is that located? Does that even exist on this model? It does not look like it exists. That is probably going to be the equivalent of this PP3V3 S5 SMC VDDA. Maybe. Let's see what that circuit looks like on an A1708. See, I worked on one the other day. Was it this one? Nope, that's an A1708. Okay, I'm glad I checked because I was about to check this SMC VDDA line, but it looks like this is actually something that is coming out. It's a reference line. So let's compare that to what this circuit looks like. Okay, so instead it's PP3VO. Okay, why did that not pull up? What's the difference? G3 hot. Well, that's right, we already talked about that. This isn't a G3 hot line, this is an S5 line on this specific unit. So, do we have 3 volts up here? And it's going to be connected to this component that looks like garbage. So we should have 3 volts up here. And miraculously we do. Okay. We have a clock and a data line. So these are supposed to be 3.3 volts as well. Now, if I had to assume, this isn't going to be a G3 hot line. This is probably going to be an S5 line. SM bus. Let's see. And if I had to assume, it's also going to be over here. Let's see what happens when we try looking up this net line. Nope, that does exist actually. Cool. And no spot on this part of the board. We'd have to flip it over here. Okay, let's do just that. I feel like we're getting closer to where our issue is. And it says that this line is supposed to be 3.3 volts. 0.9. Let's double check that. No more red herrings. 0.9. Now 0.9 is a normal voltage line, so that is a little confusing because over here on the awesome cheat sheet, it says that it's supposed to be 3.3 volts. But it's a clock line, so 0.9 does seem to be a little on the low side. And this is being generated directly from the SMC. Sorry. Then again, we also have, PP3B3 G3 hot comes through here. Let's take a look at this real fast. R5321. That's right. This isn't going to work like it normally would. So R5321. Nope, need to clear it first. R5321. R5321 is a pull-up resistor between our PP3B3 G3 hot and our CD3215A SM bus SMC4 G3 hot clock. Okay, well, let's check and see if the other side of that is 3.3 volts. It should be, because we did confirm that that line is present. Yep, we're getting 3.3 on that side. Over here, 0.9. So now what I want to make sure is if this actually is the right resistance. So it would be 1.5 kiloohms according to the schematic. And that's what we have. So that's fine. So why do we have 0.9? Why is it that we have 0.39? I'm sorry, 0.9 volts. So we have an I2C line. We have two I2C lines. And these are basically just data lines. Sorry, I'm just thinking here for a second. Let's check and see what the data line is. Data line's directly left to our same resistors, and according to that cheat sheet, it's supposed to be 3.3 volts. Now let's not take that cheat sheet entirely to heart. Let's check and see what voltage we're reading here. Be helpful if my multimeter was on. Yeah, we're getting 3.3 on this side. Actually, we're getting some power cycling. So the unit's turning itself on and then turning itself off. Okay, so it's going from 3.3 and then turning itself off. Interesting. Okay, so now we got some power cycling. Back over here, what are we getting? Are we staying at a solid 0.9? We are, instead of 3. So, being that our data line is reading 3.3, but our clock line is reading 0.9, I would assume something over here is pulling down our clock line. And it could be either something on the other side of these resistors here, or it's the SMC itself. Let's take one more look at the SMC underneath the scope, because there definitely was some corrosion. Yeah, I mean, the main corrosion we definitely have is right there. So, being that we know that we have corrosion in this area around the SMC, just like what we did with the CD3215, let's go ahead and try reflowing it. Let's actually give it a little bit more than that. So just like what we did earlier, we're going to go around, heat up the SMC like we did our CD3215, and wait for it to just dance. Alright, let's let this area cool off for a minute. So just kind of to recap where we are right now. Originally, this one was taking 19 volts on 3 of the 4 CD3215 chips. I noticed that the one that was only getting 5 volts was missing a LDO necessary for it to properly turn on, and that was the 1.1 volt LDO. Once we reflowed it, it actually started taking 1.1 volts. However, the rest of the CD3215s then start taking only 5 volts. So we've been troubleshooting, looking around elsewhere on the board to see if there's there's any pull down. We notice PP bus is no longer being present. It was present before. So I'm almost theorizing here that there was an issue with our CD3215 that was causing it to disconnect. The three CD3215s were somehow able to request the 20 volts necessary to create our PP bus, which then went through other parts of the machine to create our PP5ES5 or PP3V3S5. But now what I'm discovering is when we reconnected it, we kind of pulled everything back down. There's a lot of corrosion around the SMC. The SMC is missing or has a pull down data line, clock line, that is supposed to be roughly, it looks like it's supposed to be 3.3 volts, but now we're only getting 0.9 volts. So what we did was just reflow the SMC to kind of clean that corrosion that was underneath the SMC and see if that resolved our issue, if that's going to remove whatever is pulling down that that clock line. Hopefully we'll have 3 volts or 3.3 volts after this. That's kind of where we've gone. We've been streaming so far for about 2 hours and 10 minutes and still troubleshooting why is this board not turning on. I just hope at the end of all of this it doesn't turn out that the CPU is dead. This one did fall into a bathtub, so I don't feel like this is going to be a full board repair as much as it's data recovery. I think we're just going to be able to get it fixed long enough to extract the data, but as far as putting the board back together into the computer, chances are the LCD is also damaged from being submerged, potentially a trackpad and the battery. So this has had enough time to cool. Let's see where we're at with everything now. Let's go back to our overhead camera and see if we have any change. Still pulling the same 5 volts on this USB, 0.05 amps. And see if there's any change. Let's go back to our other CD3215 here and see if it has changed as well. Still doing the exact same thing, 5 volts at 0.05. It's just strange because we touched something on the CD3215, which then made all the other pull down from 20 to 5. Let's check and see if that clock line is still reading only 0.9 volts. Still a solid 0.9 volts. Now, what I say is very strange about that is that looks like that's a normal line. Let's just confirm with the schematics instead of going off this cheat sheet here. Let's use our brain. So, let's see. This is supposed to be PP3V3 G3 hot on one side. It goes through this resistor, which is 1.5 kiloohms. But see, then we also have our data line. So our data line is 1.5 kiloohms as well. Make sure that we were reading this properly. Let's check and see. Where is R5320 located? It's got to be one of these. It's this one. And this is pin 2 specifically. So they're both the same resistance. Yeah, so we're getting 3.3 on this side, but it's power cycling. So we're staying at a solid 3.3. I'm watching to see if this is going to power cycle. It looks like it's staying at a solid 3.3. But this side is definitely power cycling, while this side is just staying at a solid 0.9. So CD3215A, which is U3100, is what connects the SMBus SMC4 G3L clock, as well as, well, it's all kind of connected right here. We also have our U3200, yeah, we already know about this, our UB300, and our UB400. So these are all tied together. So any one of these CD3215s can actually be pulling down our power here, because we shouldn't have that big of a drop. In fact, I think we can check a voltage calculator to see what our power should be. Thing is, this isn't necessarily a voltage drop, because a voltage drop is typically two resistors with one with a ground located, but this one is just one resistor, and this is a little bit longer, so Ohm's law. So we have a resistance of it was 1.5, I believe. Yeah, 1.5 kilo ohms. And the voltage is 3. Three volts. And that's for AC. We're really more concerned for enter two values to get the other values, press calculate. So we have a 1.5. Alright. 3.3 volts, correct? Okay. Because the SMC is also talking here, so we could have an issue with our CD3215s, or we could have an issue on our SMC side as well. And since they're all connected, they're all daisy-chained connected, if one doesn't work, then they're all not going to work. So we almost have to replace them all. Yeah, we'd almost have to whip out our oscilloscope here just to measure to see if this USB XB CC1 is present. Yeah, no, the interesting thing is that the clock is being pulled down. Okay. We're not too concerned for that. What about this one? I think that goes to the other side. Yep. As well as over here. Which also talks to the... Nope, doesn't talk to the SMC. Looks like that's just where it's coming from over here. That's right. We are not using Flex Board View. I keep forgetting that. So R3042. And for those of you who are watching, I do apologize for the intermission that we have right here. I did it again. Alright, let's check and see. Right now I'm just measuring the impedance of these resistors. P241. Yeah, it looks like that's supposed to be 33 ohms. Alright, 33 there. 33 there. Alright. 33. 33. And actually, this isn't 1.5. This is 1.3. This is 1.5. Okay. So what I'm doing is I'm pulling it out of the circuit real quick just so that I can measure it one more time, make sure it's not getting pulled down with something on the other side like the SMC. Yeah, we're getting 1.5. So something's actually pulling this down. All right, I think it is donor board time. Nope. That's right. That specific donor board is right here. Okay. Let's compare this and see what our donor board has to say. Oh yeah, that's right. Whoever worked on this, because this is a donor board, so this wasn't my board. Whoever worked on this did something weird. I think they were trying to inject voltage to see where short was. Yeah, we're getting 1.5 just fine on here. Alright, I want to measure in diode mode on this board and compare it to our other board and see which side is got where it's pulling down. So, in diode mode, what do we have right here? 0.66. Right here. 0.35. Alright, those are pretty easy ones to remember. Okay. Zero 0.66. 0.35. Hmm. Okay, so whenever this is in its circuit, it drops from 1.5 to 1.3. And we did confirm with our donor board, it's actually supposed to be 1.5, so something's pulling it down. Almost like a voltage divider. Something's almost grounded, and it's acting like a voltage divider, and I've seen when that happens, it messes with the impedance of the entire circuit. Where's that? There we are. Let's put this one back. This is our donor board, just to kind of test with. Alright, so now that this is in circuit, made sure it is getting, yeah, 1.5. So something is definitely pulling it down. And in diode mode, we're getting about 0.6, which is exactly what we had anyways. Okay. Let's see what happens when we just kind of move these resistors out of the way for a moment. We'll do one at a time and see if that changes anything. And I feel like I'm going down that rabbit hole again. Now that we have disconnected that line, do we have our... It would help if we were in resistance. Do we have 1.5? We do. Okay. Interesting. So now that we've removed that, are we going to have our 3.3? Are we going to have our 3.3 volts? Yep, 3.3 volts. So something with this resistor is actually pulling down our power. And it's not the resistor itself, but it's what the resistor is connected to. Okay, so we've made a little bit of progress. In fact, actually, when we do that, what is our power at now? Okay, it's power cycling, which is to be expected. Yeah, the entire computer is just power cycling when we remove that. But we are getting 3.3 volts on our clock. So let's put this resistor back and kind of understand what is going on behind this. Okay. So over here, we have our CD3215s that we were messing around with. So this is UB40. This is the one that, or UB40, that's the name of a band. UB400. This was the one that we messed with. And then this was the one that we reflowed. And then we have our Hall sensor. What else do we have? I have a touch point. And we have a JTAG. All right. So something here is pulling down. It's probably one of those CD3215s. What about over here? These two don't really talk to each other. So it looks like that is fine. Okay, so let's revisit that CD3215. If we had to replace one, it would probably have to be this, since it's being pulled down. Because this one we put back on just fine. Now we also could have an issue with this Hall sensor. Okay, I thought we were stuck, but I think we're beginning to make some progress again. So let's flip our board back over and inspect what exactly is going on here. So this is the area that we reflowed, and it looks like that we may have exposed where our issue is, and it's pulling down our voltage to our data line that talks to the system management controller. There also is a potential issue with the Hall sensor. I don't remember if that Hall sensor was dirty or if it was the other one. One of these looked really bad. It was this one. This one looked pretty bad. Okay. So I think the next step is going to be to remove this. In fact, we probably don't even need our Hall sensor, because at this point this is just going to be data recovery. With the amount of damage that was on here, I'm going to remove the Hall sensor, and then I'll also remove the CD3215. And after that, well, I think we're just going to end up replacing it. This one did look worse than the other one, to the point that I thought that was the one that wasn't working. So this entire time, it very well could have been just a bad CD3215. So when we heated up this one, that's when all the other CD3215s quit turning on, which would make sense because it's pulling down a data line necessary for the SMC to turn on or talk to the CD3215. So now it's all starting to make sense. At first I couldn't really put my thumb on why was it that reflowing would pull everything else down. Well, they're all tied together to that one connection. Let's just pull this guy off. It looks like it was a pretty clean connection under that. So I'm going to say this is our culprit. Now that the board is hot, let's go ahead and wick up some pads. Alright, so that CD3215 has been removed. No immediate signs of damage, which makes me think there might just be an internal fault somewhere. So now that we know the computer is not going to take 20 volts just yet since we've removed the CD3215. But let's find out if that clock line for the SMC is still being pulled down. I'm curious. Let's see. Where is that located again? Here you are. So our USB-C ammeter is... looks like it might be power cycling. Yep, that's exactly what's going on. Getting solid 3.4 on that side, 3.4 on this side. So this side is actually getting 3.4 volts now. So something with that specific CD3215 was pulling down our power. The computer is power cycling, but I would imagine that's because we are missing a CD3215. So let's go ahead and replace it and see if that resolves our issue. Be exciting, because we've been going for 2 hours and 40 minutes at this point. This one has been troublesome, just because of the amount of corrosion. Once again, this one went into a bathtub. That's why this one was having so many issues. There's one solder ball on there. You can probably see it on the camera. It's a little bit bigger than the rest, so I just want to wick that up. Okay. And let's go ahead and grab another chip. Alright, now that's lined up, let's drop our CFMs. I'm pretty sure that's the technical term. Every time I see anything about fans and throughput, it's always measured in CFMs. And let's just go around, generally heat this area until we see it wiggle, then we'll crank up our airflow. Alright, so it just wiggled into place. So now what I'm going to do is apply a little bit more flux to go underneath it like that. And let's turn up our airflow. And now it's just kind of dancing around. And now to let it cool. Alright, so now let's have another recap. So what was going on is we reflowed a really disgusting CD3215. It was the only one that was only taking 5 volts. All the other ones were taking 20 volts. Once we did that, they were all taking 5 volts. So after troubleshooting, chasing rabbits, we then found out that there is a clock line necessary to turn on in order for our CD3215s request 20 volts. So if we look at this really handy cheat sheet that's on logi.wiki, we were going through these steps and we noticed that SMBus SMC4G3 clock line was low. It was actually 0.9 volts. According to this, it was going to be 3.3. Just to compare, these both come from PP3V3G3 hot, and they have the same resistor between. It's a 1.5 kilo ohm resistor. When we checked our data line, we were getting 3.3 volts, but on the clock line, we weren't. So something was pulling it down. When we went back to revisit where on our clock line was located, let's see, our clock line, we had this resistor right here connected to I2C UPCT clock 2. That is a mouthful. Once I remove this resistor, our SMBus SMC4 G3 hot is working. We're getting 3.3 volts. So something on the other side of this resistor is drawing power and pulling it down. It's a partial short, you could say. Well, when we check and see what's on the side of RB 242, there's a test point. There could be some corrosion, but I'm not really going to blame that to be your issue. But we have our CD3215s that we heated up. We heated up this side, the UB400. One named after the band, UB40. And we were thinking maybe that's where the issue was, but I think when we heated it up, we actually exposed where our issue was on UB300. So being that UB400's been replaced, well, logically it just makes sense to replace UB300. I also just went ahead and replaced our hall sensor, just completely removed it, just in the off chance that it is grounded, pulling down that line as well. And we don't need the hall sensor for data recovery. The hall sensor, what its sole purpose is every time you close the lid on your computer screen, it triggers the sensor essentially to put it into sleep mode. It's not really necessary for startup function, not like the CD3215. So the computer's had enough time to cool down. Let's see if after all this digging and head scratching, if we have made any progress. $20 volts at 0.6 amps. 20 volts at 1 amp, 20 volts at 1.5 amps. That is a successful board. So now we need to put this in the screen to see if it actually works. This one was really hard. But I hope I've demonstrated the process of going through and kind of seeing how everything connects together. Kind of like in NCIS, we'll use that as an example. One of those crime investigation shows where they have the tack board with like the red lines connecting everything together. It kind of all seems like it's starting to work. So ultimately, all the amount of corrosion that we have here on the board, the main issue that we see is that the CD32 A1707 which coincidentally is the first one I thought was bad, is bad. I replaced the second one anyways just because this one that was bad was pulling 20 volts. The other one that I thought was bad was pulling 5 volts, so it was a red herring. Let's see if this is actually going to turn anything on the display, and then I'm going to do a data recovery. I'm going to take a look at the connection on the EDP connection just to make sure that it's not damaged from the bathtub. Okay, let's take a look. Ooh, time to get some WD-40 on this microscope. Okay, so that is a little worrisome, but as far as data recovery goes, we might be able to work with that. Let's check and see what exactly that is. That might be our backlight line that connects to the CPU. If they're too close together. Okay. PPV out SO LCD backlight 43. Doesn't quite look like under the scope that these two had touched. But it doesn't look good. I'll clean it up. So this is our power, our voltage out to the LCD, and this is going to be a data line that talks directly to the CPU. So if I hook this back into the computer and the screen's not turning on, we'll know why. The fortunate thing for this specific model is it has a dedicated graphics card. Being that this is, at this point, strictly for data recovery, in the event that the voltage line for the backlight had touched the data line, it's going to take out our GMUX, which is okay because that can be replaced. But that just means that our internal display would not work. Our external display, if we were to hook up to a monitor, would be just fine though. And like I said, at this point, this is just strictly data recovery. So if we need to hook up to an external monitor just to get it working, that will be enough to get the job done. So I'm curious if this is going to turn on in the housing. Before I get the housing out, I'm going to clean this area up. Alright, let's reassemble this computer and see if the display is actually going to turn on. There are some components in here that I don't trust. It's mostly the trackpad connection, actually. One second. I think I might have another top case to put this into. No, it doesn't look like it. Let's clean up this trackpad cable. I don't know how that happened. Oh, looks like my finger hit the down arrow. All right. This one has definitely been a difficult one. But honestly, I'm very happy that we had access to the cheat sheet on Logi.wiki, because I wasn't aware that that specific line for the SMC had to be present in order for the CD3215s to request 20 volts from the charger. The wiki is very, very helpful. I know Louis Rossmann has his new wiki, which is equally as helpful as well. Just the wiki at Shiny Computers, Chris, we've been working on it for a year. Me and a couple of other technicians from the Rossmann Discord, which if you're wanting to get into board repair, I highly recommend joining Louis Rossmann's Discord. A lot of smart technicians there willing to help out. Just don't please, bro. If you're interested in actual questions pertaining towards certain repairs, you can ask there, but you can get the best help if you actually join Louis Rossmann's board forum. $30 a month. We're personally on there as well, because sometimes we have questions that I are beyond my scope of knowledge that I need to go on there and ask to Informaticos. He's very knowledgeable as well. And just the repair community in general, I really love. Everyone's here to help each other out. And at the end of the day, it's to make sure that the customer can get either a working computer or their data back after Apple had told them that their data's gone. Alright, so I'm not going to worry about connecting the battery now. I just want to see if the screen even turns on. Okay, so let's watch the meter just to make sure there's nothing in here. Okay, so we're still only pulling 5 volts when it's in the housing, which makes me think there is a connection here. It's probably the trackpad that is pulling down a line necessary for it to turn on. So let's just remove the trackpad real quick. 5 volts. 5 volts. Come on, don't let me get too excited. This turned on for a second. Okay, still not turning on. Let's see if it's because the touch bar is connected. Okay, plugging back in, 20 volts. All right, so something on the touch bar was actually preventing the computer from turning on, so now we're getting the proper amperage. Let's see if we get anything on the screen. Is that backlight I see? Yep, look at that. Working Apple logo. Now, if it boots up all the way, I can go ahead and begin the data extraction. Just gonna go ahead and cover. I want to see if the customer's information pops up. Touch bar is very finicky, and it can be shorted underneath the touch bar. There's some circuitry, and if it gets wet, it will actually prevent the computer from turning on. So after I unplug the touch bar, it is booting up. The trackpad and keyboard might be okay. In fact, actually, I'm going to interrupt the boot cycle right now just to plug the trackpad back in. If the trackpad is missing, there's a thermal sensor that can't communicate with the system management controller. And what it does as a failsafe is it makes the fan run at full speed. The computer itself doesn't want to, it's a little choppy right now, the computer itself doesn't want to kill itself. So to make sure that it's not going to die, it turns the fans on all the way, which will throttle the CPU because the fans are running so high. It makes the CPU run cooler. But in all, looks like it's coming back on right now, it'll make the computer run slower, ultimately. So when we plug the trackpad back in, the thermal sensor is talking to the system management controller and should be turning on. It's probably going to boot into password recovery mode. This is exciting. It only took 3 hours to fix this one, but this one did fall into a bathtub. So this is rather exciting. Come on. You can do it. I believe in your strengths, MacBook. Also don't have the battery connected to. I think there's a thermal sensor built into the battery. So as a fail-safe, it also throttles the CPU. It's almost there. Because I'm pretty sure there's not a thermal sensor in the touch bar. The computer should boot up just fine without the touch bar. But being that the battery's not plugged in, or the trackpad cable, while it's still plugged in, could still be damaged to where the trackpad's not communicating to the logic board. It's getting there, but it's getting there very slowly. Now we just wait. It's inching, but it is getting there. So much anticipation. Is it gonna turn on? That looks like it's booting up. Come on, give me a name. Give me a name. Oh, yes. And it works. It is alive. So for now, I'm just gonna go ahead and shut it down. Trackpad does seem to be working. Surprisingly, the computer as a whole does not have any liquid in the display, despite it being submerged. So this is really, really impressive. Let's shut the computer down. Fantastic. Awesome. That was successful. So we took a chance at fixing a MacBook that was completely submerged. Never had one submerged before. Had plenty of things spilt onto it, but never actually dropped into water. So this was a successful repair. I'm very content with this. We have a couple more repairs for the rest of the night. Deciding if I'll actually stream them or not. Various things, iPads, SSD upgrades, some more board repairs. So for those who have joined for this nice 3-hour stream, I know there was moments where it was very dull. However, I had to use a lot of brain power to try to figure out what's going on. Anyways, I'm rambling at this point. Thank you so much for joining me this evening, and I'll see you guys in the next one. Bye.